Sample and distribution model for sample proportions, p-hat. Imagine you toss a coin 10 times and record x, the number of tails in your 10 tosses. This fits the binomial model. X is binomial with n equals 10 and p equals 0.5. Suppose now that each time you toss the coin 10 times, you calculate the sample proportion p-hat of tails in your 10 tosses. P-hat is equal to the number of successes all over the number of tosses. The sample size n is 10. If you assume the coin is fair, the true proportion of tails is p equals 0.5. Imagine taking all possible samples of 10 coin tosses and calculating p-hat. Note that the sample proportion p-hat will not be the same every time. This is due to sample invariability. And then imagine graphing all these p-hat values. We have imagined the sample and distribution model for sample proportions. Recall from chapter 17 that our binomial model of n and p, our expected value would be n times p, and our standard deviation was the square root of n times p times q. For this, our expected value of p-hat would be x divided by n. The expected value of x divided by n, which would be the expected value of 1 over n times x, which would be, we can factor out that constant of 1 over n. So it'd be 1/n times my expected value of x. And we know that our expected value of x is n times p, so this would be 1 over n times p. So my expected value for p-hat would just be p. And we know this is also known as mu of p-hat. And then my standard deviation of p-hat would be my standard deviation of x over n, which then you can factor out the 1 over n. And we know that the standard deviation of x is the square root of n times p times q. And this, if I wanted to go ahead and multiply through by 1 over n, this would become the square root of npq all over n squared, which would just become the square root of pq all over n. So my standard deviation of p-hat equals the square root of pq all over n, which is also known as sigma p-hat. To make use of sample and distribution model for p-hat, certain assumptions must hold true. We will check conditions as a way to determine whether the assumptions are reasonable. So our assumptions, sampled values are independent of each other, and the sample size n is large enough. So we need to check the following conditions. Conditions to check. We need to check and state that we have a random sample condition. So the sample should be a simple random sample of a population. Sample methods not biased, and sample is representative of the population. This checks for independence, and you have to state this within context. Your 10% condition. If sampling is done without replacement, trials will not be independent. However, you can still proceed as long as the sample size is less than or equal to 10% of the population, or the population is large relative to the sample size. So you also have to check that. And then the success failure condition. The normal distribution will give an accurate approximation to the sampling distribution model for p hat, as long as n times p is greater than 10 and n times q is greater than or equal to 10. This is a large enough sample size condition. You can also see pages 394 and 395 in your textbook. So we have a new distribution with our center, our expected value of p hat, which is mu of p hat, which equals p. Our spread, our standard deviation of p hat, which is sigma p hat, which equals the square root of pq, all divided by n. And our shape is approximately normal. Let's look at some examples. This first example says, power companies killed trees growing near their lines to avoid power failures due to fallen limbs and storms. Applying a chemical to slow the growth of trees is cheaper than trimming, but the chemical kills some of the trees. Suppose that one such chemical would kill 20% of sycamore trees. The power company tests this chemical on 250 sycamore trees. Consider these a simple random sample from the population of all sycamore trees. What is the probability that at least 24% of the sample of 250 sycamore trees is killed? So first, we need to check our conditions and state what we have. Okay, so with this, I usually go through and I state P, which is 0.2, N, which equals 250, and P hat from my sample is 0.24. Next, I go to my conditions. One, you're told to assume the sample of trees collected is a simple random sample. Notice it's within context. 250 sycamore trees is less than or equal to 10% of all sycamore trees. And again, notice it's within context using the information given. Then n times p equals 250 times 0.2, which equals 50. That's greater than 10. N times q is 250 times 0.8, which is 200, which is greater than 10. So our sample is large enough. We checked all our conditions. So now we can go ahead from here and find the probability that at least 24% of the sample of 250 sycamore trees is killed. So we're finding the probability that P hat is greater than or equal to 0.24. And what we need to first do is find our z-score, our z-statistic for this. And we'll end up having to draw a picture. So to find z first, z would be p hat minus p all over the square root of p times q all over n. So this would be statistic minus parameter all over the standard deviation of the statistic. So our test statistic is 0.24, our parameter is 0.2, and then we would plug in for our standard deviation. P is 0.2, Q is 1 minus 0.2, which is 0.8, and our N is 250. You do have to show this work. So this is work you do have to show. You go ahead, you put this in your calculator, and you get 1.6. So the probability that Z is greater than or equal to 1.60. And what we can do is we can go ahead and put this in your calculator after you get it set up like this. And this would be normal CDF of negative 1E99, or it's greater than or equal to, so it would be 1.60 to positive infinity. So 1.60 to 1E99, and we would get 0.054799. And if I were to draw this picture, which you always want to do, that's what it would look like, and that's about 5.5%. So the probability that at least 25 or 24% of the sample is killed is about 0.0548. And you want to answer within context. So the probability that at least 24% of the sample of 250 sycamore trees is killed is 0.0548. And let's look at one more example. According to government data, 22% of children under the age of 6 live in households with income less than the official poverty level. A study of learning in early childhood chooses a simple random sample of 300 children under the age of 6. What is the probability that more than 20% of the sample of 300 children is from poverty households? So again, my P is 22%. My N, my sample, is 300, and my P hat is 20%. Check our conditions. A simple random sample of 300 children under 6. $300 children under 6 is less than 10% of all children under 6. NP equals 300 times 0.22, which equals 66, which is greater than 10. And NQ is 300 times 0.78, which equals 234, which is also greater than 10. So all our conditions check. So we need to find the probability that P hat is greater than 0.2. So first we need to find our Z. And to find our Z, it would be 0.2 minus 0.22, all divided by our standard deviation. And this is work that you do have to show. So it'd be 0.22 times 0.78 all over 300. And you would get negative 0.83, make sure that you draw a picture of this. So 1 would be here, negative 0.83 would be something like this, and we would want more than, so it would be that way. So in your calculator, you would have normal CDF of negative 0.83, 1E99. And if you have an older calculator or they ask you for your mean and your standard deviation, and I said that 1 would be there earlier, and 0, your mean is 0, your standard deviation is 1, and you would get 0.796731. So answer them within context. So what is the probability that more than 20% of the sample of 300 children is from poverty households? The probability that more than 20% of the sample of 300 children is from poverty households is 0.798.